All right, the final chapter of the year. So this is an interesting one because we're talking about three types of functions. One is going to be power functions, polynomial functions, and then we're going to talk about rational functions. Now I'm going to break this this unit down into more than one video, probably 3 videos, so that they'll be shorter and then you can go through and see the differences. First of all, for this video, we're going to identify the different graphs and the feature of power functions in the form y equals kx to the p. We're going to compare and contrast exponential, power, and linear functions. We're going to identify the degree and the maximum number of turning points for polynomials. We're going to determine the end behavior of polynomials of even and odd degrees. And then we're going to determine a polynomial with given zeros and a point. And we're going to find vertical and horizontal asymptote for rational functions. So that would be the last video for the rational functions. So I'm going to do power for this video with a little bit of polynomial. I'll do another polynomial, and then I'll do rational functions for the last video. All right, let's look at what a power function looks like. A power function is a function in which the dependent variable is proportional to a power of the independent variable. So remember, dependent, which is your y, in this case your f of x, is proportional to the power of the independent variable, which is x is your independent. Now I'm going to break it down to a little bit more basic terms because you guys are used to exponential. Basically what you have here is I have a constant k, so a number of some sort, a constant k multiplied by something with an exponent. Now if you look at this, if we're going to compare, let's look at what some common power functions are, is I have 2x squared. So I have a constant times something raised to a power. And if you'll notice, the independent variable is down low. Okay? And you're going to look at these and see how the x's in this case are all down low, and it's raised to a power. And the power we know, but we don't know what the variable is. Okay? So when I go to do this, you're like, okay, well, what's so different? Well, if we compare this with exponential, and exponential functions are written this way, y equals ab to the x. And do you notice my independent variable is up high? It's an exponent. I don't know what it is. Versus now, this, my independent variable, is down low. That's the difference between power and exponential functions. Now, sometimes when you graph them, especially if you look in quadrant 1, they look very similar, but power functions are different. They're much different, okay? So let's look at some even and odd and even powers. Now I know your slides might look a little different because I changed this up. This probably just says odd and even. So please, on this slide, go ahead and write these points, and we're going to talk about how do we come up with power functions. Now, again, here's my points x and y, and I want to come up with a power function. And a power function is y equals k x to the p, or the power here. So x and y are our points, the constant k, and this is our power. So what we're going to do is we're going to go through and plug in what we know. So I'm going to start with the big one here. So I'm going to start with a 13. So I'm going to say 13 equals k times 4 raised to the power, divide, and then I've got 3k 1 to the power. Now, by doing this, I say, okay, thanks for playing. The k's are gone. So now I have 13 thirds. Now, if you remember, even though my bases are different, if they're raised to the same power, I can combine these. And I say, okay, 4 divided by 1 is 4, so that's 4 raised to a power. Okay. Now, what makes this a little bit different than what you've done before, what we don't have is the power. How do I find out what the power is? Well, I have to natural log both sides. So I'm going to natural log this side and natural log this side. Now I have natural log of 13 over 3 equals, and we'll use log rules, p natural log of 4. And then I'm going to divide both sides by natural log of 4. So I have the power is the natural log of 13 over 3 divided by the natural log of 4. Now, when I put this in my calculator, I get the power to be 1.05774. So I just wrote it out a lot of decimal places. So now I say, okay, I have to come up with the whole formula. So I have this now. I have the formula so far is y equals k x to the 1.058, if you will. We'll go 3 decimal places. 1.058. Now I have to figure out, okay, what now is my constant, right? So when you do this one, I say, all right, I can just plug in one of the points. So I'm going to use the 1, 3 because it's nicer. So I have y equals k times 1 raised to a power. And 1 raised to any other power is still 1. So basically, this whole thing is 1 right here. So I have k times 1. So k actually comes out to be 3. Because this turns out to be 1. And when I divide 3 by 1, I get this. So I know k is 3. So my power function is y equals 3 x to the 1.058. So there's my power function. All right, let's try another one. All right, I have f of 7 is 8 and f of 1 is 0.7. So this is the 0.78. There's my independent dependent 1 0.7. Okay, so y equals kx to the p. And I'm going to use the bigger number on top, the bigger y, I guess, and the power in this case. I have 8 equals k 7 to the power. Divide, divide. I have 0.7 equals k 1 to the power. Thanks for playing. So now I have 8 divided by 0.7. Equals, now if they're raised, different bases are raised to the same power, I can just combine these. Well, 7 divided by 1 is 7. Raised to a power is 8 divided by 0.7. Now I want to figure out what the power is, so I'm going to natural log both sides. And when I do, I have the natural log of 8 over 0.7 equals p natural log of 7. And these are hooked by multiplication, so I'm going to divide by natural log of 7. So p is really natural log of 8 divided by 0.7 all over natural log of 7. And when I do that, my power comes out to be 1.2519. So when I plug this in there, I have y equals k, that's a k, x to the 1.2519. Plug in the easy point. I'm going to pick this one because it's a 1. So now I have 0.7 equals k 1 raised to the 1.2519. Again, 1 raised to anything is 1. So 0.7 divided by 1 is 0.7. So k actually comes out to be 0.7. So my formula, again, is y equals 0.7 x to the 1.2519. Now, I do want to show you on this, is if you look at this one right here, this is 1, 3, and it went up to 413. I want you to look at it started at 3, and the power is over 1. Okay? This one started at 0.7, and the power is still over 1. Right, because it's still an increasing function because when I went up to there. So these are both increasing functions, and this is very similar to how we found exponential functions, but a little bit different. You have to know the formula is y equals kx to the p. Right? All right, so now odd integer powers. So let's look at what an odd integer power is. Well, you have y equals x to the p, and p is odd. So p could be 1, 3, 5, 7, get it? Okay, so anytime your power is odd, this is what your graph looks like. Now I know probably on your paper I don't have this written, so if you need to stop this at any time to kind of sketch these, but you'll notice y equals x is this straight line going right here. Y equals x to the third is this one right here that I'm tracing right now, and then x to the fifth. So they kind of all have this shape except for the y equals x, where to me it looks like seat-shaped. Seat-shaped. It looks like one of those plastic seats you sit in. But I want you to notice something, that y equals x to the fifth is a higher power than x to the third. And if you'll notice, the seat's a little bit sits upright more. It's not leaning back, and it's closer to the y-axis. All right, so that's what an odd power function looks like. Like I said, stop the video if you need to copy this down. So what kind of characteristics does it have? Well, I call it seat-shaped. It's a seat-shaped function. The common points it has is 0, 0, -1, -1, and 1, 1. Concavity. Well, because it looked like this is what it looked like. When x is less than 0, it was concave down like a frown, so that would be this part right here. When x was greater than 0, which is this part right here, it was concave up like a cup. So that's how the concavity works. The end behavior. Now, end behavior is the ends of the graphs. Sometimes we call them the tails of the graph. So if we were to look at, again, this is what it looked like. The end behavior, what we're looking at is this part right here and this part. Where is my graph going? So what we typically like to say is we go, okay, when x goes to positive infinity, so I'm going this way, what are my y's doing? What's my y's doing? Well, they're going to positive infinity. If I look at this tail over here, or the end behavior here, when x approaches negative infinity, my y's are approaching negative infinity. And I want you to notice that your tails are opposite, if you will, or your end behavior. Your tails are opposite. One is going in this direction, the other one's going in this direction. And that is one of the behaviors or characteristics of an odd function, where your tails are in opposite directions. Okay? So let's look at the next one here. Now let's look at even powers. So I have y equals x to the p, and this is even, so this could be 2, 4, 6, 8. Get the idea. When you look at an even power, it looks parabolic shaped, almost looks like a parabola, but it's not really, but it looks this way. And you'll notice it's symmetric about the y-axis. Now, this one right here, this black one right here, is y equals x squared. Then I got x to the 4th and x to the 6th. And if you'll notice, the higher the power, even power, the skinnier it looks, or the closer to the y-axis. And so this is what it looks like. That's what even functions. I want you to notice that my tails are in the same direction. So if we're going to talk about these, we're going to call these U-shaped graphs. And when they're U-shaped, you could say they're parabolic shaped, which sounds like parabola. But I want you to know the true x squared is the only parabola. You can't call x to the 4th a parabola. You can say it's parabolic shaped, which looks like a U, but really the only parabola is x squared. Okay? The common points that even power functions have are 0, 0, 1, 1, and -1, 1. Concavity, and the ones that we saw, they all kind of looked like this. So they were concave up in this case. You'll see some that look like this, which are concave down later on. But notice that you'll see that my tails are in the same direction. My tails are and we're going to talk about end behavior, but they're in the same direction for both. Either they're both up or they're both down. So that goes with even powers. So let's talk about end behavior. So if we have one that's concave up like this, as x goes to infinity, positive infinity, my y's are also going to positive infinity. And as my x's go to negative infinity, over here, you'll see my y's are still going to positive infinity. They're both going the same way. And if you were this way, they would both be going to negative infinity. So basically what I want you to get out of here is that my tails are in the same direction. Now 0 power, notice I didn't put 0 power in everything. X to the 0 is 1, but basically it's a discontinuous graph. Even though you don't really see it when you graph it, you have to really zoom in, and it still might then not show on your calculator, because x to the 0, 0 to the 0, if I put a 0 in for x, does not exist. There's no such thing as 0 raised to the 0 power. So if you were to really look at this graph, which is the graph of y equals 1, you would see there's a hole in the graph because 0 to the 0 power doesn't exist. And I just wanted to have you have that for your notes, because it is kind of, I don't want to say a picky type of thing, but I wanted you to see. Okay? The next thing, comparing power and exponential functions. So we already noticed power is y equals kx to the p, and then exponentials are y equals ab to the x, or y equals ae to the kt. All right, so you're very familiar with exponential. So I want to compare the two, and we're going to be talking about what happens with it. And we use the word domination, dominates, okay? Dominates is basically saying which one gets quicker, faster, okay? So you're going to ask which one dominates, right? So that means as x approaches infinity, which one has the higher x values, excuse me, y values. Okay, so that's what it basically means. Or which function gets larger, quicker, or faster. That's what you really want to know. So I graphed here, and I made the window very large so that you could see this. I mean, it's very large. And I want to compare 12x cubed versus yx to the fourth. So you have to determine which one this is. So I see my x is down low, so this is a power function here. My x is down low here, so this is also a power function. So now I'm doing power versus power. Which one dominates? Which one gets larger, quicker? And in this case, the higher power wins. It doesn't matter. It does not matter what the coefficient in front is. The higher power is going to dominate. So in this case, this function is going to dominate or get higher, quicker. And if you look at it, I have y equals x to the fourth right here. If you'll see, after a while it crosses here and bypasses it. See how the numbers are getting larger, quicker? So after a while, now this window is huge. I can't even remember what window I used here, how big to show you that. I think this is like 1,000 or 10,000, I can't remember. But I did have someone one year say, oh, Mrs. Pond, no it doesn't. And it doesn't show right off the bat, but the larger you make the window and you keep making it bigger and bigger, you will see that this function, y equals x to the fourth, will dominate over 12x cubed. Even though the 12 is there, it doesn't matter. It's just because the other power is higher, it just gets larger quicker. It doesn't matter. Now let's compare domination with x is down low, so this is a power function, versus my x is up high, or it's an exponent, this is exponential. So we want to say which one dominates, okay? Well, if you look at this graph here, here I have y equals x cubed. Let me get down here. So I have y equals x cubed is here. And then I have y equals 2 to the x. And look what happens. Guess who dominates? The power function, excuse me, the exponential function. So this one, exponential dominates. Gets larger quicker. Well, how are you going to remember that? Exponential function dominates. Well, how you remember it is, there's a lot of ways, but I always say E comes before P in the dictionary. Okay, so there's something, that's how I remember which one dominates. And the exponential function will always win over a power function because it does get quicker, faster, and it always does. Doesn't matter what your coefficients are, it does. So let's look at a couple here. I'm going to put it on this slide here. And we're going to compare. So let's do an example right here. So I'm going to do a couple that you have here. So here's example 1. I have this function. So this is my first function. And here's my second function. You got to tell me which one dominates. So I'm going to make like a little table here. So for the first one, I have 0.005, 1.04 to the x. And my other function is 1,000,000 x to the 1,000. Okay? And my second one I want you to see is I have 0.002 x to the half, and I have 1,000 x to the negative 2. So if I look at these two functions here, this is a function here and here, I look at this one and I say, oh, my x is up high, this one's exponential. And this one is x is down low, so this is a power function. Which one dominates? Well, you would think this does because it's got a million, it's raised to 1,000, but it's not. It's the exponential. This one is going to grow quicker, faster, because it's exponential. I don't care if there's decimals here or whatever. After a while, this will dominate. Always does. Now let's look at the second one. I have this power function here because my x is low. I have a power function here, and I want to know of the two which one dominates. Well, the higher power wins. A half is bigger than -2. Even though this has 1,000 in front of it and this is 0.002, it doesn't matter. You just look at the power. So I just wanted you to see that to make sure that you could make sure that you knew which one dominates. So power, two power functions, it's the highest power. Exponential function and power function is exponential every single time. Okay? Now let's talk about some polynomials. First of all, I want to know what a polynomial is. Well, they're the sum of power functions. So all I'm doing is taking a bunch of power functions and adding and subtracting them with whole number exponents. There are no square roots of exponents, no fractional powers, and no variables in the denominator. Each power function part that is being added is called a term. Okay, and we've talked about this before. So here I have all polynomials can be written this way. A sub n x to the n plus a sub n minus 1 x to the n minus 1. And this looks really nasty, but all this really is something like this. Your degree of your polynomial has to be greater than 0, and these are coefficients. So when I had something like this, 3x cubed plus 7x plus 4, that's a polynomial. Because this is a term, this is a term, this is a term. And if you'll notice, the powers are descending. This is just the math way to write it. So if you see my power that went from 2 to 1, so it's written that way, and these are my coefficients in front of each one of them. So that is what a polynomial is. So you've been doing polynomials all right along. I can have as many as I want. I could have y equals 7x to the 5th plus 4x to the 4th minus 3x squared plus 2x plus 10. I mean, that's a polynomial. You just have 1, 2, 3, 4, 5 terms. Okay? And how you come up with what the degree of the polynomial is we're going to look at this next one. So to figure out what the degree of a polynomial term is, it's the power of x in the term. The degree of a polynomial is the highest degree of any single term. The leading coefficient of a polynomial is the coefficient of the term with the highest degree. So this is what we do. So quadratic has a power of 2. That's the highest power. We call them quadratic. The highest power, if it's x to the 3rd power, is going to be cubic. Quartic would be x to the 4th. Let's put this x squared here. And then quintic is x to the 5th. All right, and I know you can have x to the 6th and x to the 7th, but I just thought I would give you kind of what you call it. So we call it a cubic equation if you have x cubed is your highest power, quartic if it's x to the 4th, quintic if it's x to the 5th. Okay? The next thing we talk about is the number of terms in a polynomial. As an nth degree polynomial turns at most n minus 1 times. So this is what I'm going to show you. Let's look at a parabola. So I'm going to draw a parabola, happy face parabola, opens upwards. This is a polynomial. Okay? Now, if I want to know how many turns I see, it just turns once. It has one turn. Well, a polynomial that is a parabola is an x squared. Do you see that it has one less turn than the power? Okay? So if I had a 9th degree polynomial, which means that's my highest power, which is like x to the 9th, I would have 8 turns in my graph. Up to 8 turns. Okay? If it was an 8th degree polynomial, I would have 7 turns. Get the idea? So I don't really want you to memorize this. I would just think of this. Think of a parabola, say, okay, it has 1 turn, has a power of 2. So then you'll remember your turn is 1 less than the power. So if I was looking at this polynomial, first I know it's even because my tails are the same. And so I just count the humps, if you will, the turns, and then I would know the power. 1, 2, 3, 4, 5, 6, 7. If I have 7 turns, that means that, and it's even because I can tell by looking at it because my tail's in the same direction. 7 turns means this is an 8th degree polynomial. Okay, so that kind of gives you like a little heads up of what's going on. So what I'm going to do now is stop this video because I'm going to show you in your packet you'll have a grid that I want you to fill out, but this is the beginning of powers and polynomials, and I'll see you in the next video.